on this subject is needed. Then the last subject that we covered in the lab, how to relate it to spin polarization and different multiplicity. Then several things that characterize the material: density of states, absorption spectrum. Here, the most challenging subject, the dispersion and dependence of energy as function of k vector. We didn't cover it yet, and it is a plan for coming Tuesday lab section. And here are, we are going to cover it on April 2nd. How to launch a thermal motion for a model. How to make the model to perform molecular dynamics. And is it possible to represent the motion of ions in the model in form of movie? And is it possible to bring it out to the rest of the world to some sort of video publishing? If I would need to make a presentation, I probably would select this one. Oh, and I have forgotten one. We need to plot orbitals, right? So it should be also in the list. Lucky number 13. Plot Kohn-Sham orbitals.
Using paths.
Okay, and as soon as we complete this part, we will be fully equipped to do independent research. It is enough to create some valuable publishable results. Sometimes they're not super precise, but they bring helpful information. Common. It's not yet an academic part of our meeting. We are going to select some subjects for independent research. And I'm just sharing opinion. It is so easy to get lost in the directories in running multiple jobs. And please try to think ahead, how are you going to organize your directories? Because it is very bad idea to run several jobs in the same directory. So for each specific experiment, you need a specific directory. And you may get an idea how many directories you may need for a single model. So each model can be modified electronically by looking it in the neutral state without spin polarization in ground state, the simplest thing. Then you may excite it. It will be another stream of directories. Then you may just consider it in spin polarized situation. And then you can ionize it by creating anion or cation. And for each of those streams, you may want to have a separate directory for running the thermalization, molecular dynamics, for finding density of states, for finding spectrum, those k points, and specific directory for orbitals. Orbitals. So it is 5 by 1, 2, 3, 4, 5, 6, about 30 directories per model. It's not very scary. Sometimes you do not need all of those tests, but it is a think ahead how you organize, how you design names of directories so that you can navigate through them easily. And it will make your life much more pleasant. Subjects for independent research. The original idea that everyone selects subject of research independently. So please, you're very welcome to do whatever you like. Just apply knowledge of the course to what is interesting, to what you do in the experimental lab, or what you were curious for last 10 years but didn't have time to explore. But if you have a little lack of idea, or if you can choose between several, I will be happy to make some suggestions and help with their implementations. So it is not obligatory, it is not requirement, it is just a suggestion what can be chosen for the independent project. Basically what I would do if I would be in class, I would select maybe one of those 14. Salvated ions, metallic ions with water, many water molecules. One water molecules out of those can be ionized, and it can bring some features into electronic structure. This could be interesting. Then interface between metallic and semiconductor nanostructures, particles, and we have a person who is trying to do these things actively. Then quantum dots that are specific for creating semiconductor lasers. The photovoltaic is based on the concept, and electronics based on concept of p-n junction. Modeling of p-n junction could be an option, and I already have some models prepared, so it will be one step less, doing exploration rather than building. Doping of and co-doping of materials. Putting some aromatic dyes on a surface of metal could be a project. Then modeling the reaction of combustion of fuel and oxidizer in a real time can be done, and it was done as a part of one of the independent projects year and a half ago. And there are several other projects. If I do not want to waste time of them, please feel free, switch on your imagination, and we will finalize your projects next week. Okay, so for the academic part of the meeting, we are not going to bring anything new. We're going to summarize the concepts that we have considered last time and just arrange them in a such logical way that it will be comfortable to program, to implement in a code. Before I start talking about this, I'm going to distribute materials. So probably it would be best if you just take one and pass it further. So the one I'm distributing right now is a famous book by Parent Young, and anyone doing exploration of density functional theory making reference to this book. And the second one, I want to play open cards. The one I was using for preparing last 3 lectures. So it is a little oversimplified text, which is standard for physical chemistry courses era Levine, but it has a very good summary of density functional theory in an amount of material that one can get in a reasonable time. And let me know if I didn't print enough copies. I can just communicate them personally or upload to the detail. Okay. So we do have about 3, 4, 5 very simple equations that we can take as a take-home message from our last lecture, from our last meeting. So we can agree, we did agree, that total energy of a model can be expressed as a functional of charge density, right? No objection. And the benefit of this formula, of this idea, is that one can replace calculation of all details from actual first principles by making up an simplified analytical formula which is sometimes related to Taylor expansion, so that energy does depend on density distribution. In the simplest case, it will be some integration of density over all space. In more complicated cases, it will be a little bit more advanced formulas, and hopefully the Tuesday speaker will entertain us with a little bit more details of the functionals I built. But this is very efficient, numerically efficient way. Efficient. And the procedure is basically it is a fitting formula. It is really all functionals are, in some words, are fitting formulas, and they work really quick. Then, as soon as one does have a functional, one can apply the concept of functional derivative. So instead of energy, getting something that may later act on the wave function and serve as an operator. And this potential can be expressed as functional derivative over density of this total energy minus kinetic. Any objections? Any questions? Okay, so the benefit of this formula is that we do have a path, we have a way to return back to standard problems that one was solving for many years in quantum theory for finding one electron eigenstate problem. So we are converting back to operator language. Then we were talking last time that bigger multi-electron Hamiltonian with some specific approximations used in Kohn-Sham theory can be represented as summation of single electron small Hamiltonian, and even they use lowercase h for this one electron Hamiltonians. And there, this potential and kinetic energy operator can be combined and serve for finding one electron orbitals. Here I use this theta letter, which is theta analog of Latin and English. Oh, English th. Is Greek letter theta. And there is no specific reason other than following the notation in the one of those handouts. So that if you go back, you see the same notation. So this is very simple, very affordable eigenstate equation for one electron orbitals. It is quick, simple to solve. One electron eigenstate equation. Did we cover any other material last time? We were considering how to convert bigger multi-electron wave function into one electron charge density. It represents all electrons. And we made a little discovery. Well, it is not really discovery because it was made years ago by others people, but we have found actually ourselves that the density, depending as a function of one independent variable, one position, representing all electrons, can be expressed as a summation of all these orbitals, absolute value squared, the second orbital, absolute value squared, plus as many orbitals, as many electrons we have in the system. And this is also a little wonder that instead of complicated multi-electron, multi-variable functions, we have a simple construction. We should admit that it is simple. And the biggest benefit that we can interconnect these four items, these four constructions together, and make them depending on each other. So the last one generates the first one. And then we go in a cycle way, in a repeating way, and repeating the whole calculation. This density enters here and determines the total energy. And then back, total energy determines the potential determines the orbitals, and orbitals determine the density. So it is this connection of these four concepts is referred to as Kohn-Sham theory. If someone asks you what is Kohn-Sham theory, you can either show these four formulas or tell by words what you understand about them. Okay. Let me distribute the same page as we had on the screen in a printed form, and it will be a little help in completing quiz that we are going to do in a couple of minutes. Could you please pass it further? Okay. So what you are having in the printed version is same equations, same formulas. So they are just typed in a little better way than handwriting. And what we are going to do is to consolidate those formulas in a flowchart to show their mutual connections, to show with arrows what follows from where and where we have branching points, right? So if we look back into one of our meetings, we were introducing the dictionary for building flowcharts that one has those round-angled boxes for input or output. Then one has square blocks for mathematical operations, and if there are some branching points, some conditions, then one in, two out. Those diamond symbols represent branching. And in this Kohn-Sham procedure, we do have a branching. We repeat this cycle-wise procedure until the total energy at previous step of iteration becomes equal to the energy on the next step of iteration. And since it is a numerical procedure, two numbers cannot be absolutely equal. So instead of being absolutely equal, previous minus total energy next, they should be smaller than some limit, some tolerance limit. So if one can set up this limit very, very small, like 10 to the minus 20. And if the difference of two numbers is less than very small number, then they are considered numerically equal. Right? On other hand, if we are not targeting super champion class precision, but we are limited in resources, we can play with this tolerance limit, set it much more generous, and complete calculations in shorter time, in less cycle. So here is the quiz. So please write your name in the corner and try to fill those boxes with the formulas from another piece of paper.
त्यो दुईजना चाहिँ के हुनु अरू कुनै पनि पाएन
So please start doing it as you can right now, and we all should be able to complete it in 5 minutes, I think. Just repopulate those boxes with formulas from previous page and make arrows.
Dr. Gillen?
Yes?
What about us?
On the SDSU side, you can draw same boxes just in your notebook and try to populate them.
Okay.
I'm going to start collecting your quizzes in 2 minutes. Okay, I will be going across and collecting works. Now that I actually have another space. Okay, thank you very much for completing those unexpected quizzes. And let's design a key and answer for this thing by filling it one person per box. So Mohammed, would you please come up here and help me filling it? So let's not everything, just please fill the output box. What would you put there? Okay. Very good. And what does it depend on? Okay. Total energy as a function of density. Very good. Thank you. So there is a little important detail for computation. So at the output, we need this total energy also as a function of our model of our system. If we model one molecule, another molecule, the result should be different. And molecule is specified by positions of ions, right? We also need to say that the total energy depends on position of all ions in the model. Okay. John, would you come here and help to populate the first box? Yes. Where we start from? Yes. Yes. It is. Okay. What else? No. No. Positions of electrons. Electrons are clouds. We don't. Maybe number of electrons. Because each specific molecule is characterized by position of ions and number of electrons. And what else? For our previous comment before we started quiz, we proceed until the total energy on the previous and next run become equal. And we need criterion of this equality, so some tolerance limit. We call it epsilon tolerance. Perfect. Thank you much. May I invite Vino? So box number 2. Before we start the cycle, our first formula for total energy and for potential depend on some density. But here at the beginning, we do not have any density. So we need to get it somewhere. And we can use a random number generator or maybe computed by lower level method and just right here guess initial density. Very good. Yeah, thank you. Yuchi, would you please come and help to continue? And here is a little easier part. So now, as soon as we do have the guess for initial density and for immediately provides guess for initial total energy, you can probably set up the potential. Excellent. Will you please help me making arrows between them? So from input we go to guess, little arrow here. Then from guess we go to this one. Okay, yeah. Thank you very much. Would you please come and help continue? So what do we do after we do have a potential? Yes, yes. Excellent. Thank you much. So this equation that Chang introduced help us to find orbitals. Shelton, would you please come and help to continue? So after we have established these orbitals, what can we get out of them? Yes. So the orbitals do help us to find density. Let's write it down. And you see the upper limit that Shelton is putting there in the formula, in the summation. It does appear from one of our input data. So we need this input data number of electrons because we need to know how many of those orbitals are occupied and how many of those orbitals later will help us to build the total energy and complete the cycle. Thank you very much. Very good. And we have one little step to complete. Stephanie? Yes. Yes. Just the one we wrote on the previous slide, that total energy previous and total energy next is less than tolerance limit. You can maybe make index I+1. Be creative. Okay, and would you also please help to make arrows to yes, go back and to this box, right? It is true. We go here. Okay, thank you very much. So it is a brainstorming session that brought us to redesign Kohn-Sham algorithm. So we are checking if we achieve the convergence limit, and if it is true, then we report our total energy as function of what we put initially, of number of electrons, tolerance limit, and positions of ions. If it is not true, we repeat the same cycle again and again. And as long as we go through the cycle, our total energy, our total density, and our orbitals are slightly changing because they depend on each other. But they are changing consistently. And therefore, one often refers to it as self-consistent procedure. So it is not diagonalization of matrix. It is one repeats until all parts of the game are consistent. Perfect. It is something that you can take with you and quote it in your papers if they have computational fragment. It is a really valuable thing. And here is approximately same data with a little bit better typing. So we have maybe 10 minutes more, and now I want to go out of box. So right now we are starting with positions of ions. They are fixed. We are solving only for electronic problem. And through this Kohn-Sham procedure, which we can enclose in the box, we start with positions of ions, and we end with total energy of the system. But if we look back on what we did 3-4 weeks ago, we were discussing optimization of geometry. We were discussing finding the best interatomic positions, best set of positions for given set of ions. And we were already designing the algorithmic way to refine them through finding points on the potential energy surface, through finding gradients, where to move on this potential energy surface, where to contract or elongate orbital bonds, distance between ions. And we were also building self-consistent cycle to improve interatomic positions. As a part of this procedure, we left a black box. That was meaning that from somewhere, we do not know where, we are getting total energy of the system as function of positions. So this was, I think, lecture number 8, and it is what we were drawing. So we started with geometry, tolerance, and step size, and then we were computing gradients and increment of each position, of each ion. And then we were recomputing the point on the potential energy surface. Point on potential energy surface. And then, if it was bringing us some improvement in total energy as a function of positions of ions, we were reporting that mu geometry is better than previous one. And if it was not bringing enough improvement, we were repeating the procedure. But in this algorithm, we did have a black box. So we didn't knew what is here. But now we have a powerful tool to put something inside this black box. The quizzes that you completed and what we our brainstorming session gave us a module, a subroutine that starts with position of ions and generates total energy with reliable, precise enough electronic structure calculation. So now this module, this subroutine, can be inserted into this black box and used for geometry optimization. So not focus. Fill the black box. Fill the black box with DFT. Okay. So I was doing a silly thing. I was redrawing the same geometry optimization thing and just enlarged the size of this box. And now we are going to merge, put in your quizzes right into this place. Right? So it is a Kohn-Sham procedure for finding total energy. So this U as function of position. And now this is a schematic, this is a plan to encode the computational chemistry software. So as soon as we have this thing, we can just, not using Gaussian VASP, we can just buy Fortran compiler, sit and write same thing. And the core of this code will be 2 cycles. One cycle in the subroutine to refine the electronic structure that starts with geometry and ends with total energy. And second cycle that refine the position of ions, that do geometry optimization. So there are 2 cycles that one is inside another. And the rest are technical details. And step that we get optimized geometry. And for this optimized geometry, we do know electronic structure. And then we can compare it to experiment. So we have geometry, and we have total energy, and if you want, we have some other details, like density of states, absorption spectrum, ionization energy, whatever is needed for dipoles, level of charge transfer. Okay, I think it is the main message. Let me maybe summarize it in verbal form. So we have one cycle for improving geometry, another cycle to improve electronic structure, and the electronic module is serving as a module for finding a point at the potential energy surface and to navigate through potential energy surface to find the right geometry, the correct geometry, the optimal geometry that does correspond to realistic system. So we did build the algorithm for encoding DFT and for optimizing geometry. It helps us to understand how codes are working. By understanding how they're working, we can operate codes more efficiently, and we can immediately recognize that probably one needs 2 tolerance limits. One tolerance limit for geometry and another tolerance limit for electronic energy. And this gives us more flexibility and versatile approach to running the codes. We can understand possible errors. And then with this algorithm, we can go beyond geometry optimization. We can go into molecular dynamics and predicting chemical reaction. Okay. Next time we do functionals, and next Thursday we do presentations on VASP. please, I need this single piece of paper with your names about what you select for. You have it. Did everyone sign on this piece of paper? No? Okay. So with this, I'm open to questions. Are there any questions? If there are no, then meeting is dismissed. Thanks for coming.
अर्को पालि भने नेक्स्ट क्लास
Next class.
Put your name where you want. Put your name where you want. And if anyone didn't put the name on this piece of paper, please do it now.
केटाहरूले पढाएको धेरै बुझिन्छ